For many years, industrial cybersecurity was built around one assumption: the industrial system exists inside the plant. That is, controllers, HMIs, engineering workstations, and networks were physically located within the operational environment. So the security was focused on segmentation, isolation, access control, and protecting the OT network boundary. But industrial environments are changing. Today, organizations are connecting sensors, deploying edge devices, using cloud analytics, and introducing AI driven capabilities. So, this creates a new question: where does the industrial system actually exist? Imagine a railway condition monitoring system. Sensors installed on equipment collect operational data. An edge gateway processes and forwards this information to a cloud analytics platform. Machine learning identifies abnormal behavior and alerts maintenance teams before failure occurs. Operationally, this creates huge benefits, but from a cybersecurity perspective, the architecture has changed. The system is no longer just the equipment in the field. It now includes sensors, gateways, communication paths, cloud platforms, applications, and third party providers. So, where does the OT boundary actually end? This is not just an architecture question. It affects the risk assessment, the zones and conduit models we define, and the responsibilities we assign. This is the kind of challenge addressed by Part 1 6 of the 62443 standard. For years, practitioners have used the Purdue Enterprise Reference Architecture or the Purdue Model to organize industrial functions. But Purdue was developed as a functional model. It was not originally intended to be a complete cybersecurity or network segmentation architecture. Over time, however, we often began treating its levels as though every function lived on a predictable physical network layer. But OT challenges this thinking. A cloud platform may only provide analytics, or it may allow operators to view and manipulate equipment, or it may automatically influence control decisions. These are very different risk profiles. The important question is not, is it IT or OT? The important question is, can this capability directly or indirectly impact the physical process? IEC 62443 requirements extend into the cloud environment when cloud based functionality can directly or indirectly change the physical state of the equipment under control. When assessing IIoT systems, I think about four simple questions. First, what does this capability actually do? Is the technology collecting data, analyzing it, advising an operator, or controlling equipment? Second, what data or commands move between systems? What data or commands cross each trust boundary and in which direction? Third, what happens if it is compromised? What happens if the data or service is manipulated, delayed, or unavailable? Fourth, who owns the security responsibility across the ecosystem? Who operates it? Who patches and monitors it? Who approves changes? And who recovers the service when it fails? Because with IIoT, cybersecurity is no longer just about protecting a network boundary. It is about understanding the entire system. IIoT is not making traditional OT cybersecurity obsolete. The fundamentals remain: risk assessment, segmentation, secure communication, identity management, and lifecycle security. But the architecture is evolving, and IEC 62443 provides a structured way to secure this new reality. Because the future of OT cybersecurity is not just about protecting devices, it is about protecting functions, processes, and the physical world they influence. In the next episode, I will explain why not all IIoT and AI use cases in OT creates the same cybersecurity risk. Till then, stay safe, stay secure, and I'll see you in the next vlog. Peace.